Well, hello everybody. Welcome to another wonderful day of Math 211. So today what we're going to be doing is going over the homework from chapter 9 and 10. That was direct proofs and proof by contrapositive, so that we could spend some time working together on those things. I've already seen some questions in the chat, and I appreciate that. Thank you very much. If you have more questions or other numbers you want to go through, let me know. I'm going to start off with those, and with whatever time we have left, I'll go through some of the others. So, we'll go ahead and get started. And the first question we had was chapter 9, number 8 and 20 from chapter 9. So we'll go over number 8 here. Alright, so what we have here is if x is a real number. So let x be a real number if it is the case that x to the 5th minus 4x to the 4th that big long equation is greater than or equal to 0, then it has to be the case that x is non-negative, that is greater than or equal to 0. So how are we going to prove this? Well, let's go ahead and go up to the board. Now, the idea here is that we're going to work by a proof by contrapositive. And so what that means is we're going to start with, we have an if-then statement. So we had if P, then Q. And so the contrapositive would be if not Q, then not P. So when we're setting this up, just like we did with direct proofs, we're going to begin by writing assume something, and then we're going to have then something. So you want to keep in mind what we get to assume and what we have to show. And we're going to start at both ends and try to make these work. So if I assume not Q, Q in this case is, I'm just going to look to make sure I write this down correctly, x is greater than or equal to 0. So the negation of x is greater than or equal to 0. That's what we're looking for. That's what we get to assume, is x is a real number and less than 0. So we assume that x is a negative number. Then what we have to show is not p, where p was x to the 5th minus, I have to look at it a little bigger to make sure I get this big equation, minus 4x to the 4th plus 3x cubed minus x squared plus 3x minus 4. And the original statement was that that was greater than or equal to 0, so we have to show that this is less than 0. So if we negate greater than or equal to, we get less than. So I know I ran out of room here, but I have to show that this big long thing is less than 0, assuming x is less than 0. All right, any questions in there so far? All right, very good. So now the idea, or what I want to point out here is that, first off, if I take something like 3 is less than 4, then if I take 2 plus 3, it should be less than 2 plus 4. So I'm having to remember some properties here, but if I substitute the 3 with the bigger number 4, and if I have something like 2 plus 3 and I substitute in the bigger number, then the result is going to be bigger. So if I know 3 is less than 4, then 2 plus 3 is less than 2 plus 4. Therefore, if x is less than 0, then I can write something like 2 plus x is less than 2. So this isn't part of the proof. I'm just trying to give us a guideline of what's going on here, is that I'm going to use this idea that, okay, if x is less than 0, then 2 plus x is less than 2 plus 0, because I can substitute in the bigger one, and my result will be bigger. The way I'm going to use that then is I'm going to say, okay, x to the 5th minus 4x to the 4th plus 3x cubed minus x squared plus 3x minus 4 is going to be less than. Well, notice that I'm going to use that same idea here, and I'm going to substitute in what I know about x to the 5th. Well, if I have x is less than 0, so if I raise a negative number to the 5th power, then I'm going to get and I want to think about it, is it going to be positive or negative? Well, negative number to the 5th power is negative, so this is a negative number. Therefore, this is less than 0. So I can write that this is less than 0 minus 4x to the 4th plus 3x cubed minus x squared plus 3x minus 4. That is, I know that because x is negative, x to the 5th is negative, therefore this term is less than, I can substitute in bigger number for x to the 5th, and I get a bigger number. And actually, that's what we're going to do the whole way, is just say, well, then that is less than, and so I have the 0. Now, in this case, I want to be careful because a negative number to the 4th is positive, but I multiply by negative 4, so I end up with a negative number, so this whole term is negative. So instead of subtracting some number, I'm adding 0, so this whole thing ends up bigger on this side if I have 0 instead of this negative number. Same thing here, x cubed is negative, times a positive 3 is still negative, so that is less than 0. X squared, a negative squared is positive, but I'm subtracting it, so it's negative, so that's less than 0. 3 times a negative number is negative, so that's less than 0. Negative 4 is less than 0, so I can substitute in a bunch of zeros. In the end, what I get is 0 plus 0 plus 0 plus 0 plus 0 is 0. So what I have is, well, if x is less than 0, then term by term, each of these terms is going to be less than 0. So if I add a bunch of things that are less than 0 together, I'm going to get something that is less than 0 plus 0 plus 0, which is 0. Hence, if this is negative, this whole thing has to be less than 0. And so then that's going to be the proof there is, once you realize kind of that, oh, I just need to realize this portion is negative, so I can say this whole thing is less than 0 plus the remainder, it really just follows through by saying each of these you can substitute in a 0. Now, just as a note before moving on there, is if I had even one place where that wasn't true, say this was a plus, then this one, I would end up with something like this. I can't actually end up getting that that's less than 0 because I don't get out 0 here because I don't know what's happening here, and this may be somewhere where that's positive or something like that. And so if I have something where not all of the terms are less than 0, I can't necessarily get this proof out. And so the whole point is that if we look at this proof, each of the terms was set up so that if I plug the negative number in, I got a negative number so that my proof follows out fairly quickly. And that's the type of thing that I would put on a test. If you start mixing pluses and minuses, then it becomes a much more complicated problem, and it would be something you would do in calculus by finding all these zeros and then making a number line. But finding all the zeros of a 5th degree polynomial is not the type of thing that we would do normally. It's the type of thing you'd have a calculator do. Do you have any questions in there? You're not understanding the zero stuff? Alright, so I'll just focus one term at a time. I know x is less than 0. If I take x to the 5th, what is really happening here is this is some negative number. Let's say y to the 5th, where y is positive. So what I end up with is I negative 1 to the 5th times y to the 5th. Because x was negative, so I'm writing this so that y is positive. So this is just going to be some positive number, but if I take negative 1 to the 5th, I get a negative number. So I get a negative something, let's say z. Because this is negative, any negative number is less than 0 by definition. So the negative number is less than 0. That's why this term is less than 0. And then if I continue through this, so the x to the fifth is less than 0. The x to the fourth is positive, so if I multiply by 4, it's negative, so it's less than 0. Same thing here, this term is less than 0, this term is less than 0, this term is less than 0, and negative 4 is less than 0. So the whole thing just becomes less than 0 plus 0 plus 0 plus 0. Does that help out? All right. That is actually a common problem on that one, is overthinking. It's really just, once you notice that each of the terms are 0, everything has to be less than 0. The reason why it's in here is not so much to test that part, and if you see that, it becomes really easy. The hard part is, it just wants to make sure that you're okay with this contrapositive thing. If you try to show this directly, that is, if I showed that this was greater than or equal to 0, to show that x was greater than or equal to 0, this is an extremely complicated proof. So there's not a nice way to kind of do this. You really have to come up with something very creative to get from here to here. But the point is because we're using the contrapositive, if we notice to use the contrapositive, it makes a complicated proof into a pretty easy proof. That is, once we realize, oh, hey, this just has to be negative, each of these terms is a negative, we're done. That's not a hard proof to do, as long as, again, you don't overthink it. But if you try to go the other direction, it's an extremely difficult proof, which is why they put it in here, just to kind of highlight that fact, the utility of a contrapositive proof. All right. So that was number 8. The other one I had a question on was number 20. So we'll look at that one. And what we have here is, suppose that a is an integer. If a is congruent to 1 mod 5, then a squared is congruent to 1 mod 5. All right, we'll go to the board for this one. All right. Now I just want to, maybe you guys can help me out here. I just want to make sure I did it right. Was it if this, then that, or was it the other direction in the book? If it's the other direction, let me know, and I'll do that proof after we're done with this one. But I want to do this one to begin with, because I think it's an interesting proof. All right. Now, if I want to do, if a is congruent to 1 mod 5, then a squared is congruent to 1 mod 5. I could try to do a proof by contrapositive, but that's going to seem weird because I'm going to say a squared is not equal to 1. So even though this is in the section about contrapositive, I would use a direct proof here. And so we do always have the option to use any proof we want. And so I'm going to say assume a is congruent to 1 mod 5. And then what I have to do is I have to say then a squared is congruent to 1 mod 5. All right, now what we have here is we have to remember something from our last lecture when we're talking about modular arithmetic. And there's a couple things that we proved. One was that a is congruent to b mod n. So a is congruent to b mod n if and only if n divides b minus a. Now another thing that we proved was that if we have A is congruent to B mod n, and C is congruent to D mod n, then AC is congruent to BD mod n. And these are both theorems that we proved this last time, so this we'll call theorem 1, and this we'll call theorem 2. I know it's a little sloppy here, but what I have was we showed that A is congruent to B mod n if and only if n divides B minus A. So that's what this is saying, is that instead of writing A is congruent to 1 mod 5, we can say this is equivalent to saying 1 minus A is divisible by 5. But we also showed that if A is congruent to B and C is congruent to D, then AC is congruent to BD, which means that modular arithmetic respects the multiplication. That is, we can substitute in what each of those things are when we multiply. Now, if we use this one, our proof actually follows out very quickly. And how am I going to do that is, well, I know A squared is, or A is congruent to 1 mod 5. So A squared is equal to A times A mod 5. Because A squared is just A times A. But what we know is that we can replace these numbers with things they're congruent to, because modular arithmetic respects the addition. So I can just write A is congruent to 1, A is congruent to 1, mod 5, but 1 times 1 is just 1, mod 5. And so actually this one follows out, if we just use our modular arithmetic, this one follows out very quickly. A squared is A times A is 1 times 1 is 1, and then we're done. That makes that really easy, doesn't it? So if you get used to using modular arithmetic, it really does come in handy when we're dealing with things like these. On the other hand, if you don't use that, what you're stuck with having to use is that you have to say that this is congruent to 5 divides 1 minus A. And what I have to show is that 5 divides 1 minus A squared. Well, so again, I'm writing by definition these things are equivalent, which means that 1 minus A is equal to 5k1, and I have to show 1 minus A squared is 5k2 for some integers k1 and k2. So that is, if I didn't want to have to actually use modular arithmetic, this would be the process. You can definitely do it this way, it just takes a little longer. Now, what I would do from here is I have to show this assuming this. So I'm going to need some more room. So what I'm going to say is 1 minus A squared is equal to, and now notice that this is the difference of squares, so I can factor that. This becomes 1 minus A times 1 plus A. But we just said that 1 minus A was divisible by 5, so it was 5k1 times 1 plus A. Now, what we get is that k1 is an integer, 1 is an integer, A is an integer, so 1 plus A is an integer times an integer is an integer. So we can just let k2 equal k1 times 1 plus A. And we get that 1 minus A squared is 5 times k2. So therefore 5 divides 1 minus A squared. So A squared must be congruent to 1 mod 5. So those are two different ways of doing that proof. All right. Now, just because I think this is an interesting proof as well, is let's suppose that A squared is congruent to 1 mod 5. Can we show that A has to be congruent to 1 mod 5? So our proof, I'm going to do this directly. Assume that A squared is congruent to 1 mod 5. And I have to show then A is congruent to 1 mod 5. Now actually, I'm going to do this one by contrapositive. So I'm actually going to assume that A is not congruent to 1 mod 5, and I have to show that A squared is not congruent to 1 mod 5. And so that's why I wanted to do this one, is because then I would actually use a contrapositive. I'd actually have a negation. So A is not congruent to 1 mod 5. I have to show that A squared is not congruent to 1 mod 5. That would imply that if A squared is congruent to 1 mod 5, then A is congruent to 1 mod 5. Do you guys have any questions on what I'm doing here? Is this making sense? All right. Now here's the tricky part, is that when you say things are not equal to something, that means it's equal to anything else. The reason why that works here is because there are only 5 things that A can be congruent to mod 5. So what we end up with is 4 cases where I'm not congruent to 1. So I would say case 1, A is congruent to 0 mod 5. Case 2 is A is congruent to 2 mod 5. And then case 3 is 3 mod 5, 4 mod 5, and then I would have all my cases. So I would start with A is congruent to 0 mod 5. If A is congruent to 0, then A squared is congruent to, well, I can substitute in 0. So I get 0 squared mod 5 is just 0 mod 5. Because 0 is not equal to 1, A squared is not congruent to 1 squared mod 5. If I work with 2, 2 squared mod 5, then A squared is 2 squared mod 5, which is just 4 mod 5. All right. I'm just going to substitute it in because I'm going to run out of room. What am I up to is 3. If I have 3, then A squared is 3 squared. 3 squared is 9. But if I divide by 5 and take the remainder of 9 from 5 is just 4. So then 3 squared is congruent to 4, which is still not 1. The last one I have to check is 4. So if I'm 4, I get 4 squared, which is 16. Oh, so we actually can get that this theorem would be false, because 4 squared is indeed equal to 1 mod 5. So I guess I was wrong on this one. It does work out that you can have something that is not 1 mod. A squared is not congruent to 1, where A squared is congruent to 1 mod 5, but A is not 1. That is, we could use 4. So there's a counterexample. All right. So that one didn't work out quite the way I wanted it to, but I did want to go out to here is that you can actually do things like this where you break it up into cases. If you say, well, if it can't be this, what can it be? And so I can work out each of these cases. And there are proofs like this where, okay, where it's not 1 mod 3, so therefore it has to be 0 or 2 mod 3, so therefore what do I end up getting? So I have to think about what each of those are going to be and what it's going to look like. So that's a good example anyway, even though it didn't quite work out the way I wanted to, because it gives you some proof techniques that you can use in other examples as you look in the homework in other sections. So does that mean the theorem as a whole is false? This theorem, as written right here, is false. So that is false. Because we showed the contrapositive was false, but the contrapositive is logically equivalent to the statement. Therefore, this statement as a whole is false. I'm just going to leave it there. Does that make sense? All right, good. Now that's also foreshadowing because later on we will have to determine if theorems are true or false. And so that's kind of the process we'll have to go through too. But we'll get to that later. So don't worry about all the details here. I just wanted to illustrate the whole by cases thing so that you can get used to seeing that, because that does show up in some of the homework. All right, do you have any other questions that you guys specifically want to go over, or should I just pick some that look interesting? All right, so I'm just going to look at these. If you guys want to go through the whole proof of this, just tell me, otherwise I'm going to step you through it. So if x is odd, then x cubed is odd. How would we do that one? Now, because we're in Chapter 8, this is a direct proof, so we're going to assume x is odd. I have to then show x cubed is odd. So what does it mean to be odd? It means that x is equal to 2k plus 1, and I have to show x cubed is equal to 2k2 plus 1. And so if you do the arithmetic there, or if you use modular arithmetic, this actually follows fairly quickly. Nobody's really saying you want to go through this one, so I'm assuming you got it. So I'll move on. You did have a question about 14 here. Thank you for that. Alright, so what I want to show is that if n is an integer, then 5n squared plus 3n plus 7 is odd. Very good. Let's go up to the board then. Let n be an integer. Then I want to show that 5n squared plus 3n plus 7 is odd. Alright, so now as I start this one, what I'm going to notice is that if I'm just assuming n is an integer, I don't know what to do there. I don't know how to work with that because I don't really get to assume a lot. There's no definition there. It's just, okay, n is an integer. We're good. That's all we get. So they don't really give us a lot. What we have to prove is that this is always odd. So I'm going to start from the bottom and say, what does it mean to be odd? So what does it mean to be odd? It means that this is not even. It also means that 2 does not divide 5n squared plus 3n plus 7. But since 2 does not divide that, that means that 5n squared plus 3n plus 7 is equal to 2 times some integer. We'll say k1 plus 1. And it also means that, well, if it is even, we show that that meant it was congruent to 0 mod 2. So it's also equivalent to saying 5n squared plus 3n plus 7 is congruent to 1 mod 2. Now, I haven't finished the proof. I have a lot more to fill in. But I didn't know where to start, so I just started writing down whatever I knew. I'm going to write down definitions. Saying that this is odd is equivalent to saying it's not even, is equivalent to saying that 2 does not divide it. That is, if I divide by 2 using the division algorithm, the remainder is going to be non-zero. Since it's non-zero, it has to be 1. Which means that if I take this mod 2, when I divide by 2, the remainder will be 1. So if I can show any of these, I get that this is odd. And because I have so many different ways to write odd here, if I can show any of these, I get this out. And so that gives me a lot of different options, a lot of different ways to try to prove this. And so I have to work through and say, well, which one do I think will be easiest? And there are indeed multiple ways to do this proof. I'm going to show you at least one, if not two. But if you come up with some other way, as long as you end up showing that one of these things is true, that's good. And I'm actually going to stick with working with my modular arithmetic for now. So I'm going to say that saying that this is odd is equivalent to saying that 5n squared plus 3n plus 7 is congruent to 1 mod 2. Now, I just picked that one because I like it. If you liked one of the other ones, you can pick those. There's nothing wrong with that. But what I want to point out here is that now that I've picked that one, I want to pick something or know something about the integer so that I get this out. Now, if I take any integer, since I'm looking at things mod 2, what I want to know is what could any integer be mod 2? Well, I don't have an exact answer here, but what I have is that either n is congruent to 0 mod 2, or n is congruent to 1 mod 2. Because when I take anything mod 2, it's either 0 or 1. Those are my only options. So I don't know which one it's going to be, but I know it's one or the other. Now, what I have is I get to assume an or, and I have to prove a statement. So what does that mean? Well, that means I have to use cases like I was trying to show in the last one. And case 1 will be assume that n is congruent to 0. I have to show this. Case 2 would be n is congruent to 1. I have to show this. If I can show that both times, what I get is that, well, if it's congruent to 0 or 1, which means it's anything, then this has to be congruent to 1 mod 2. Therefore, that has to be odd. So as long as n is an integer, we get this as odd. So we actually have two proofs here. We have this is case 1 and this is case 2. So I'm going to start with case 1. Let n be congruent to 0 mod 2. Then what I get, well, now I could talk about how this means that 0 minus n is divisible by 2, and I could use that reinterpretation. But I'm going to use the fact that we know that modular arithmetic respects multiplication and addition, so I can just substitute in what each thing is, mod 2. So maybe you guys can help me out here. What is 5 congruent to mod 2? Well, if I take 2 and divide by 5, I get 2 times 2 is 4 plus 1. So 5 mod 2 is just 1. So what I can do is if I'm doing modular arithmetic, I can replace the 5 with the 1. What is n congruent to mod 2 is, well, in this case, we're assuming it's congruent to 0, so we get 0 squared. So I plug in 0 for n, and then we're squaring it. Plus, 3 is odd, so it's congruent to 1 mod 2. N is congruent to 0 mod 2 by our assumption. And 7 is congruent to 1 mod 2. So the nice thing here is I don't have to do a lot of algebra. I just have to substitute in what each one is mod 2. 5 is 1, n is 0, 3 is 1, n is 0, 7 is 1. Now if I calculate this, I get 1 times 0 plus 1 times 0 is 1. It's just 1 mod 2. So in this case, I got that 5n squared plus 3n plus 7 was congruent to 1 mod 2. And then we're done. That means that that's out. So we have case 1 proven. We're not quite done with the whole proof because we still have to prove case 2. So what is case 2 going to be? Is, well, I'm going to work through a similar thing here, except I'm going to work with n is congruent to 1 mod 2. So I'm going to start with 5n squared plus 3n plus 7 is congruent to, and now I'm going to do the substitution all over again. 5 is congruent to 1, but this time n is congruent to 1, so I get 1 times 1 squared, plus 3 is congruent to 1, n is congruent to 1, and 7 is congruent to 1 mod 2. And again, I do my calculations. I get 1 times 1 is 1, plus 1 times 1 is 1, plus 1 mod 2. But 1 plus 1 is 0 mod 2, plus 1 is 1 mod 2. So again, I get out 1 mod 2. Therefore, if n is congruent to 1 mod 2, 5n squared plus 3n plus 7 is congruent to 1 mod 2, which means that this is odd. Now, I've therefore proven that this is odd no matter whether this is congruent to 0 or to 1. Therefore, for any integer, this is always odd. Does that make sense to everybody? Questions at all in there? All right. The one thing I do want to point out is that if you wanted to use, say, another technique, you could say something like 5n squared plus 3n plus 7 is equal to, well, if it's even, you can substitute in 2k. And now you can simplify this, and you want to show you get 2 times some integer plus 1 after you simplify. If it's odd, you want to show this is equal to 5 times 2k plus 1 squared plus 3 times 2k plus 1 plus 7. And if I simplify this, I want to show that it's equal to 2 times some integer plus 1. Now we get, okay, well, whether this is odd or even, then this is also odd. This is how I would do it using my definition that even is 2k and odd is 2k plus 1. And this just takes a little, it's the same process, but it involves a little bit more arithmetic, a little bit more algebra. So it takes a little bit more time than trying to get used to using modular arithmetic. Now, if you don't like modular arithmetic, this technique is fine. It works. I'm happy with it. But if you get used to the mods, things just go a little quicker. That's why I worked through that one, because I feel like you're probably a little less comfortable with that. So Andre, the 1 mod 2 for 7, so their substitution is actually, this is 1, say 1 squared plus 1 times 1 plus 1. And so actually we're substituting in 1 for all of them. And when we write the mod 2, that applies to the whole thing. That's not just to the 7, doesn't become 1 mod 2. 5 becomes 1, n becomes 1, 3 becomes 1, n becomes 1, and 7 becomes 1. But I have to remember that I'm working mod 2 overall, so I put that at the end to say everything's still working mod 2. All right, good. I'm glad I cleared that up. So now, please go over number 6. I'm sorry, which chapter was number 6 you were talking about? Chapter 8, thank you. All right, I'll go back to number 6 then. So what I have here is, what I have here is, in this case, I get that a, b, and c are integers. And here I get to assume that a divides b and a divides c, and I have to show that a divides b plus c. So again, this is going to be a direct proof. I'm actually going to give you guys a second to work on this one. What should I assume? What do I have to show? Can you write down some definitions, that type of thing? I'll end up going through it with you in, a minute here, but I'll give you a minute to try to set it up. You don't have to do the whole proof, but try to say, what do I assume? What do I have to show? Can I rewrite these using definitions? How would I connect these things? So try to get as far as you can, and then we'll work on it together. All right. So if you've got it, tell me what should I assume and what do I have to show? So remember that we're in chapter 8, so we're doing direct proofs. So we're going to assume the if part, and the if part is we get to assume A divides B and A divides C. So that's the if part. The then part is A divides B plus C. So somehow we have to get from assume this to then this. All right. So if I'm going to assume this, I want to rewrite what this is. And what this means is if A divides B, that means that B is equal to A times K1 for some integer K1. And C is equal to A times K2 for some integer K2. So I'm using the 1 and 2 because I'm going to have multiple integers here. But just by definition, if A divides B, that means that B is A times an integer. If A divides C, then C is A times an integer. So I'm just writing those definitions out. If A divides B plus C, what we want to show is that B plus C is equal to A K3 for some integer K3. So again, I'm working my way both directions. What does this mean? This means this. I get to assume this. I have to show this. This is equivalent to this. So if I can show this, I'm done. So somehow I have to use this to show this. Now this one's similar to a lot of the ones that we have is because we have an equation. So we're going to start on the left and we're going to want to work out till we get to the right. So I'm going to start with B plus C. Now, what is B plus C equal to? Well, here we're going to substitute in. B is just A K1. C is A K2. So I get B plus C is A times K1 plus A times K2. So actually, I can factor out an A, and I get K1 plus K2. Well, what does that mean? Well, we notice that K1 is an integer and K2 is an integer. So if I just let K3 be K1 plus K2, then I know that K3 is an integer because it's an integer plus an integer. Hence, B plus C is A times an integer. So B plus C is A times K3. But by definition, that means A divides B plus C. So we get our theorem out. Now, the point I want to make here is that if we walk through this one step by step, assume this, show this. The assumption is equivalent to this. The then is equivalent to this. Okay, I have to show this. I'm going to start on the left and get to the right. Okay, I substitute in and I work my way through. If I take this one step at a time, it's not too bad. But if I just try to start from, okay, A divides B and A divides C, I have to get this. There's a lot that happens in there. So you don't want to try to do it all at once. You want to focus on just this portion, then just this portion, then just this portion, and just this portion. Because the little steps are a lot easier than trying to do everything at once. The little steps still aren't easy, but they're a lot easier than doing everything at once. Does that make sense? Did that one help? Any more questions? All right, so let's see. We did 14, we did 8. Did anybody want to look at chapter 9, number 12? Oh, good. Someone just asked for it. That means I get to do it. Yay. All right, so chapter 9, number 12. What we had here was, I think it was written slightly different in the book, but it said if a squared is not divisible by 4, or that symbol there is 4 does not divide a squared, then I want to show that a is odd. So let's go ahead and do that. And we're going to work this very similar process as we figure out what we assume, we figure out what we have to show. And again, because we're in Chapter 9, though, I do want to work with a proof by contrapositive. I should make a comment there is eventually I will want you guys to be able to figure out what type of proof to use. However, as far as the tests go for this class, I do suggest a type of proof. You're welcome to use a different type, but I'll say it is suggested you use contrapositive here. If you do a direct proof correctly, you still get full credit. I just try to pick the easiest one as I see it. And then on the test, I'll suggest that to you so that you don't have to come up with it. In time, you'll be asked to make sure that you understand, well, what proof should I, or what type of proof should I use and why? But that's more for later classes. All right. So getting back to this one, if I want to assume the contrapositive, what I have is, okay, it says if 4 does not divide a squared, then a is odd. So I'm going to negate the then part. The then part is a is odd. So the negation of a is odd is assume a is even. And the negation of 4 does not divide a squared is that 4 divides a squared. So because it's a contrapositive, I'm negating these. So I'm going to say assume the then part, or the negation of the then part, a is not odd, which is a is even. And I have to show that 4 does indeed divide a squared. All right. Now you could somehow use modular arithmetic here, but because we have different divisors, it gets a little weird. So I'm going to just use the formal definition of divisors. And I'm going to say that, well, if 4 divides a squared, that just means that a squared is equal to 4 times some integer. Let's call it k1 for now. And if a is even, that means that 2 divides a, which means that a is equal to 2 times, since I use k1, I'll use k2. So by definition, this just means this is equivalent to saying a squared is 4k1, and this is equivalent to saying a is a multiple of 2, or a is equal to 2k2. All right, and I think that's all I need now. Now I just need to fill in the middle part is, well, a squared is equal to, notice a is 2k2, so a squared is 2 times k2 squared. So I get 4 times k2 squared by actually squaring it out. So I get 2 squared is 4, k squared is k squared. But notice that k squared, or k2 squared is just an integer. So I'm going to let k1 equal k2 squared. And so what I have shown is that a squared is 4 times k1 for some integer k1. Therefore, 4 divides a squared. Hence, if a is even, 4 divides a squared. And therefore the contrapositive is also true, so if 4 does not divide a squared, a must be odd, because it cannot be even. So again, step by step, write out what is the negation of the then part, what's the negation of the if part. What is that equivalent to by definition? What is this equivalent to? And then we're going to try to work on the left side, substitute some things in so we get out the right-hand side so that we finally get our theorem. Yes, we could say that a is congruent to 0 mod 2. So to be even, that's equivalent to saying a is congruent to 0 mod 2. But what we want to show here is that a squared is congruent to 0 mod 4. So I'm using different divisors here. Here I'm using 2, and here I'm using 4. So we haven't really talked about how to convert from mod 2 to mod 4. And so if I write that one out, it's not a bad way to try. But as I've tried this, I noticed that I'm changing the number at the end of the mod, and we haven't talked about how to do that at all because it is actually more complicated than it would seem. So at that point, I would say I'm not really sure what to do here, so it kind of falls apart. So I'm going to go back to my different definition and use the division definition. I definitely like trying this. That's a good thought process to say, hey, let's put this down and see what happens. And that actually brings up a point is that don't be afraid to get these ones wrong, guys. I mean, that's part of the proofs. You're going to get them wrong. You're going to get them wrong multiple times. You're going to say, what should I try? Should I try this? I don't see how to do that. Should I try something else? I don't see how to do that. But then one of those ways might have been the right way you should have done it. So it really just takes practice. It takes getting it wrong over and over and finally getting it right. I know I make these look easy, but I've done these before, so I know the answer. So if you know the answer, it's easy. But if you have to figure it out, they can take a long time. Don't get frustrated by that. That is part of the learning process. That's what we want. We want you to fail so that when you finally succeed, it is that much more worthwhile. All right. Any other questions? I think we covered everything except for the first one nobody seemed interested in. Do you have questions on anything we went over? Anything else you wanted to ask about? All right. Well, if you guys don't have any more questions, I know we still have time, but I am not trying to force us to go super fast since we're online. So I'll let you guys go early here if there are no more questions. And otherwise, I hope you guys, get the homework done. Make sure to turn it in by tonight so you get credit. I need to do at midnight. We have most of the answers here, so you can just watch the video again if you need to look over the answers. But otherwise, I'll see you guys on Thursday so we can talk about new stuff, more proof techniques. All right, thank you for coming.